Very warm welcome to today's IMechE webinar organized by the Thermofluid Group. The webinar is given by Dr. Francesco Coletti and is entitled Design Monitoring and Predictive Maintenance of Heat Exchanger Networks in the Industry of 4.0 Era. A few words to introduce today's speaker. Francesco is the CEO of Hexxcell Ltd, which is a spin-out from Imperial College London, and is specializing in the analytics and predictive maintenance technology for heat transfer systems. In terms of his education, he holds a laureate degree in chemical engineering from Padova University in Italy and an MSc in process systems engineering, as well as a PhD in chemical engineering from Imperial College London. Francesco has a very broad experience. He's been working in academia, in Fortune 500 companies, as well as startups. He has published numerous articles, 70 journal articles and conference proceedings. He has co-edited the first monograph entirely dedicated to crude oil fouling. And he also holds a part-time senior lectureship at Brunel University London. He's also the executive editor of Heat Exchanger Design Handbook and holds the position of Secretary of the UK National Heat Transfer Committee. In addition, he's also a scientific committee member of the International Heat Transfer Conference. And without much further ado, I'll pass on over to Francesco to his seminar.
Thank you, Carola, for your kind introduction. Before we dive into it, I'd like to give you a brief background on who we are and what we do at Hexxcell. We started off in 2013 as a spin-out of Imperial College London, acquiring technology developed in the college as a part of a large research project sponsored by the UK government with over £2 million. The project focused on improving the design, monitoring, operations and maintenance of heat exchanger networks in the process industry, and in particular in our refineries. We are now an independent private company and a team of dedicated chemical, mechanical and process systems engineers with a knack for data science and a passion for solving complex problems. We provide digital solutions to our global customers for the design and predictive maintenance of industrial thermal systems. Before we dive into it, I'd like to give you a brief background on who we are and what we do at Hexxcell. We started off in 2013 as a spin-out of Imperial College London, acquiring technology developed in the college as a part of a large research project sponsored by the UK government with over £2 million. The project focused on improving the design, monitoring, operations and maintenance of heat exchanger networks in the process industry, and in particular in our refineries. We are now an independent private company and a team of dedicated chemical, mechanical and process systems engineers with a knack for data science and a passion for solving complex problems. We provide digital solutions to our customers for the design and predictive maintenance of industrial thermal systems. The talk today is really about Industry 4.0 and how heat exchangers fit into this revolution. When Professor Klaus Schwab, the founder of the World Economic Forum, coined the term the Fourth Industrial Revolution in 2016, he described it as the technological revolution that is blurring the lines between the physical, digital and biological spheres. The first industrial revolution started in Great Britain in late 1700s. It was powered by steam generation and led to mechanization, the creation of factories and a booming textile industry. From the late 1800s, the second industrial revolution was marked by mass production and the advent of electric energy. In the second half of the last century, the invention of semiconductors, electronics and computers brought the third industrial revolution. Today, Industry 4.0 sees the connectivity of cyber-physical systems through the Internet of Things and the use of powerful algorithms such as artificial intelligence deployed on the cloud to provide solutions that were unthinkable just a few years ago. Industry 4.0 truly opens up a world of opportunities. Internet of Things is already used today to prevent overstocking and understocking on inventory. Big data is used with artificial intelligence for quality control and fault detection. The US Navy is using additive manufacturing to produce replacement parts on ships without having them to return to port for service.
Petrochemical companies are using advanced robotics to inspect confined spaces without risking human lives. Augmented and virtual reality provide effective training and remote guidance to operators. So my question today is, how do heat exchangers and heat exchanger networks fit into this new industrial revolution? I start off with a short introduction discussing the status quo, moving on to how we can leverage data available, artificial intelligence and the cloud, to improve the design, monitoring, operations and maintenance of heat exchangers and heat exchanger networks. I'll then illustrate this approach with two case studies using refinery data. Heat exchangers are everywhere in the process industry, and they're used for heating and cooling needs. They are instrumental for energy recovery, which enables plants to unlock significant savings. They are considered the workhorse of the process industry, and as such, they're expected to just work. However, they can become serious bottleneck for production, as they are still subject to the same issues such as leakages, vibrations, and crucially fouling, as they were after the first industrial revolution. Despite their importance, and possibly because we have established design and monitoring methodologies that we trust, they've received very little attention as a part of the Industry 4.0 revolution. But since it's not what you don't know that gets you into trouble, it's what you know for sure that just ain't so, allow me to take us back on how these established and trusted heat exchanger design and monitoring methodologies work, and let me point out some of the flaws and what we can do now thanks to the latest technologies available today. The main focus of this analysis will be on fouling, as this is the main focus of the presentation for reasons that will become apparent later on. Established design methodologies have not progressed much since the Q equals UA delta T log mean, where U is the overall heat transfer coefficient and A the heat transfer area. What typically happens, for example in the process industry, is that the process engineer decides the inlet and outlet conditions needed from a heat exchanger with a specific duty. The heat exchanger design receives this specification and designs a heat exchanger with a certain area A. The problem is that when the heat exchanger is put into operation, it starts fouling. The way fouling is typically accounted for is by adding a certain fixed number, the fouling factor, that accounts for an additional resistance to heat transfer in the overall heat transfer coefficient. These numbers are available in the literature, for example from TEMA, the Tubular Exchanger Manufacturer Association, or provided to the designer by corporate guidelines. Very often, these fouling factors are used because they are perceived in industry as safety factors that prevent the heat exchanger from degrading its performance over time. However, when introducing these fouling factors in the overall heat transfer coefficient, U decreases, and since we still need to deliver the same heat duty as before, we now need to have a bigger area and therefore design a bigger heat exchanger. However, this increase in the area not only increases capital costs, but it typically results in higher temperatures and lower velocities, which are very often exacerbating conditions for fouling. The overall result is that the heat exchanger fouls more. So we go back to the drawing board and we add a bigger fouling resistance because we thought that the previous value used was not big enough. And guess what? We end up with an even bigger heat exchanger which fouls more. This is what is referred to, and it's not my own definition, as the self-fulfilling prophecy in heat exchanger design. From a monitoring perspective, we take the plant data, inlet and outlet conditions, and the geometry of the heat exchanger, and we calculate a fouling resistance by essentially using the same equations and the same assumptions that we have seen before for design, producing the well-known graph showing the evolution of a fouling resistance over time that I'm showing here on the right-hand side. So what are the issues with this approach? Well, it is clear from looking at the plant data that fouling evolves over time. So if you design a heat exchanger using a fixed fouling factor, you're neglecting the dynamics of the fouling process itself, as you're assuming that the fouling resistance is the same at time 0 when the heat exchanger is put clean into operations, and at the end of run when the heat exchanger is actually fouled. This approach has been severely criticized in the past, since not only the origins of these fouling factors, particularly the thermal ones, are uncertain, but also because they were generated at the time, for example, when the average refinery run was much shorter than it is today. In fact, in the 40s, when the first TEM edition came out, the average run was 3 months long, while today refineries tend to run for 4 to 5 years in between major turnarounds. From a monitoring point of view, this graph is commonly used by operators to assess the performance of the heat exchanger, the amount of fouling build-up, and to detect potential problems. For example, in this case, some people may look at the trends and use a linear extrapolation to represent the expected behavior of the heat exchanger. Once the measured value diverges from this extrapolation, they may infer that there is a change in the fouling behavior and may take operating decisions accordingly. However, let me show you how the fouling resistance can be very misleading and how it only represents part of the picture. For this particular heat exchanger, we were able to calculate the thickness of the fouling layer as well as its thermal conductivity, shown below the fouling resistance. The results of this analysis show that actually the problem in the heat exchanger was generated way before the time shown by the fouling resistance itself. In fact, what was happening during this period was that an upset in an upstream unit, the desalter, generated a rapid fouling event in the heat exchanger, accumulating material at a much higher deposition rate and a higher thermal conductivity than previously experienced. However, this event is not detected by monitoring the fouling resistance alone, since we now have a thicker deposit layer at a higher thermal conductivity, which, from strictly a thermal point of view, it produces the same overall effect of a smaller layer at a lower thermal conductivity. It is interesting to see how, once the problem upstream of the heat exchanger has been resolved, the period in blue here, and the type of deposition going inside the heat exchanger went back to normal, this is when the fouling resistance starts to show a deviation that can be misinterpreted as an issue. The key takeaways here are that fouling resistance can be misleading. It does not account for the hydraulic impact of fouling, it does not say anything about future performance, and cannot quantify the economic impact that fouling has on operations. So can decisions based on this quantity be trusted? Let me stop right here before we move any further and introduce one specific application that I would like to use for the rest of the webinar as a case study. This is the preheat train in a refinery atmospheric distillation unit. This is the first unit that the crude oil encounters when it's processed in the refinery. Here, the oil is heated up from room temperature to about 300 degrees C in a train of heat exchangers that is used to recover heat from the hot products of the distillation column. At the end of the train, the oil enters the furnace where it receives the last jump of enthalpy needed to reach the desired inlet distillation temperature, around 350-360 degrees C. As the oil is heated up in the train, chemical reactions generate insoluble species that deposit on the surfaces of the heat exchangers. As a result, the heat transfer is decreased and pressure drops increased. At the plant scale, what is seen is that the inlet temperature of the furnace decreases over time. Therefore, we need to burn more fuel and related CO2 emissions increase. Moreover, when the furnace reaches its limit or the pressure drops in the network exceed the maximum allowable ones, production is reduced. The problem I just described, fouling in refinery preheat trains, is a very big one on a global scale. It's estimated to generate 2.5% of man-made carbon emissions, equivalent to aviation, and cost to small refineries upwards of $1 million per year in fuel alone. When production losses are experienced, this cost can raise up to $10 million per year. These are significant savings opportunities which could be tapped into if we were able to better design, monitor, operate and maintain heat exchangers. However, we've seen how existing methodologies are flawed. Therefore, our ability to tap into these large numbers hinges on the capability of accurately predicting fouling as a function of operating conditions, fluid processed, and time. Unfortunately, fouling predictions are not easy. This is because they are system-specific, they depend on fluid, process conditions, surface conditions, and there is often a lack of fundamental understanding of the underlying processes generating fouling, which makes deterministic modeling very difficult. For this reason, some people have tried to compensate for this lack of understanding by throwing artificial intelligence at the problem. However, this is more of when I have a hammer, everything is a nail type of situation. The problem is that, although we live in the era of big data, industrial plant measurements for heat exchanger networks are often missing and can be not in enough quantity to train machine learning models, making artificial intelligence ineffective or potentially unusable. This is particularly true for independent refineries, for example. They have data from only individual plants. So on one hand, artificial intelligence plug-and-play does not work for predictions of fouling, but it does give unprecedented insights into operations if used properly. On the other hand, deterministic solutions of fouling predictions are not easily scalable and are very system-specific. Our approach is to combine the best of the two worlds. We develop digital twins and deploy them in the cloud, providing accurate health check on the status of the network and predictive insights on future operations. That is, predictions on both thermal and, importantly, hydraulic impact of fouling. The hydraulic part, often neglected, is crucial to have a complete and accurate information to rely on for decision making, especially when the plant is hydraulically limited. Moreover, prescriptive maintenance provides specific information to the operator via simple-to-understand dashboards on which heat exchangers to clean, when to clean, and how to clean it. So let's see what can be done by using data to better design heat exchangers. We have seen the limitation of the use of fixed fouling factors at the design stage, and we said that artificial intelligence plug-and-play does not work. So if we want to go beyond this, what do we use? There is experimental evidence that there are certain conditions of temperature and velocities at which fouling does not occur. What I'm showing here is an example for crude oil fouling from Kunzen and others, where they ran an experimental facility and determined the conditions at which certain crudes were fouling and those at which they were not. The threshold is shown in red on the right-hand side and can be represented with an equation that will therefore provide values of fouling as a function of process conditions and time, instead of using a single fixed number that lumps together several assumptions. The existence of this threshold can be used to determine the conditions at which a heat exchanger does not foul. Above the threshold, the heat exchanger is in the fouling region. Below it, it does not foul. The trick here is that knowing where the threshold is allows us to move the design point of a heat exchanger from above the threshold to below the threshold. However, there is no such a thing as a heat exchanger operating the design point. What I'm showing here on the x-axis is the shear stress, and on the y-axis the film temperature for 5 heat exchangers over a period of time. Each dot represents a day of operation, getting brighter with time. Colors indicate different heat exchangers. As you can see, each heat exchanger changes operating point over time. This is both because of the changes in inlet conditions from operations and because they are affected from fouling. So if we want to apply this concept to eliminate fouling, we should make sure that the heat exchanger is operating above the threshold at all times during operations. Luckily, we have operating data, and together with the information on geometry of the heat exchanger and the dynamic models that allow us to predict fouling, we are able to propose a new heat exchanger design, go back in time, replay history, and assess how the new proposed design would have performed had it been in place in the previous years of operation. We are answering questions like, which is the heat exchanger that would provide the most benefit if retrofitted, or what are the long-term benefit in retrofitting with a more expensive technology in terms of fuel consumption in my specific plant. This is really a four-step process, whereby we take past plant data, we run detailed analytics, and assess the impact of fouling on operations from both a thermal and a hydraulic point of view. We identify performance issues, potentially diagnose causes of fouling, calculate the reference conditions with no fouling, which enables us to quantify its economic impact, as well as identifying which are the heat exchangers better suited for retrofit. In the next step, plant data are used to estimate the fouling model parameters so that we can be confident in the predictions and that we are correctly capturing the fouling behavior over time. The following step is the selection of alternative options to test, for example, new configuration of one specific heat exchangers or different network arrangements. And then we use the plant data with our dynamic simulations to assess these options and stack them against each other. So let me show you a case study for a European refinery where we studied a retrofit option. This is a 120,000 barrels a day refinery where we identify E05 as a potential candidate for retrofit. This is a shell-in-tube heat exchanger with a 2-shell, 4-tube pass, 1-inch diameter tubes. And we propose to reduce the number of passes to 2, but change the outer diameter of the tubes to 3/4 of an inch. We also reduce the number of tubes and the shell diameter. So to answer the question, how will this new geometry perform, we first go back in time and assess how it would have performed had it been in place 4 years ago, when operation restarted after a major turnaround. This approach allows us to estimate the trade-offs between capital and operating cost, return on investment, the ROI, using actual data from the specific plant, not generic assumptions that may or may be not applicable to that specific plant. What I'm showing here is the comparison between the duties of the two designs. The black line is the original configuration, 4-pass 1-inch tube, and the red line is the proposed retrofit with 2-pass 3/4 of an inch tubes. You can also see here that there have been some cleaning actions which have also been seamlessly simulated. It's interesting to see how the performance of the two designs changes over time and diverges as fouling builds up. This shows that the proposed retrofit is more resilient to the buildup of fouling in terms of its thermal performance. Overall, the new design provides 3 megawatt average increase in the duty. If you look at the hydraulic performance, it's clear that the clean pressure drop in the proposed retrofits are higher. However, over time, because of the reduced fouling rates, the pressure drop in the proposed retrofit becomes actually lower than those in the original design. Very often, high shear designs that produce higher pressure drops are discarded on the basis that this may affect production. However, this shows that the higher shear design does not necessarily penalize the overall hydraulic performance, and as a result of better fouling mitigation, it could end up being the lower delta P option at the end of run. In fact, while the tube shear stress are indeed much higher than in the original design, as shown on the left-hand side, the higher shear keeps the fouling thickness, shown on the graph on the right, 70% lower than in the original design, thus reducing the overall hydraulic impact. Now, what I've shown you so far, the 3 megawatt savings produced by the new design, is based on the analysis of an individual heat exchanger. However, it's well known that changing the design of one individual heat exchanger in a network inevitably affects operations and performance of the other heat exchangers in the same network. In this case, the shell side fluid in E05 flows also to the shell side in E02. Therefore, a better performing E05 produces lower inlet temperatures on the shell side of E02. We now have a higher temperature on the tube side of the top branch, branch 1, and lower performance on the lower branch, branch 2. Here I'm showing just this. On the left-hand side, we have the outlet temperatures of the two branches in the original design, black for branch 1, purple for branch 2, whereas on the right we have the same graph for the proposed design. This clearly shows that the retrofit increases the heat recovery in branch 1, but reduces it in branch 2. Interactions are not limited to heat exchangers directly connected to each other, but they do have a knock-on effect also on other heat exchangers in the same network. This is in terms of inlet temperature and flow distribution across the branches, which in turn impacts the fouling behavior. Therefore, these interactions can be non-obvious, let alone being able to quantify them. These dynamic simulations allows us to do just this, quantify interactions and benefits of a new design as a part of the entire system. So what is the overall impact of the new design on the furnace when we consider the entire network? The redesign is estimated to save 2 megawatts at the furnace, which is ultimately what you're interested in, as opposed to the 3 megawatts estimated when we consider the heat exchanger in isolation. This reiterates the importance of considering all the dynamic interactions in the network when performing this type of assessments. Now, what we consider so far is the case in which we changed the configuration of a shell and tube heat exchanger, but we kept the heat exchanger type the same. However, this analysis can be done with alternative technologies as well. For example, twisted tubes, helical baffles, welded plates, and so on. In this table, I'm showing a summary of the various cases for this particular refinery. Unfortunately, I'm not at liberty to disclose which type of heat exchangers these are, but it's clear that if you pick the wrong type, it can be counterproductive and have negative effects on the overall performance of the network. For example, alternative technology A, reported on the third row of the table, shows a throughput loss of $4.5 million, which means that in this case, the increased pressure drop generated by this configuration were too high and resulted in reduced throughput. However, other technologies have the potential to provide significant savings. In the case of alternative technology B, for example, this accounted for over $3.6 million. So the key messages here are that the plant data can be used successfully to assess performance of alternative designs, but you need to be careful which design you pick to avoid loss in production or being too close to hydraulic limits. Moreover, this analysis should be done taking into account all interactions, thermal and hydraulic, between different heat exchangers in the network. If you want to read more about this, we have a different case study recently published with Repsol using our dynamic retrofit test, which is available on Heat Transfer Engineering, and I put a link to the article here in the QR code. Now, let's see what can be done from a monitoring and predictive maintenance perspective. But what is predictive maintenance in first place? Well, here we have one of the definitions. Predictive maintenance involves monitoring the conditions and performance of equipment during normal operations to reduce the likelihood of failures, minimizing plant downtime, thus optimizing productivity and increasing revenue. But what does it mean really in heat exchanger networks? Well, predictive maintenance in heat exchanger networks involves the monitoring of fouling and its impact on plant economics, including fluid consumption, related CO2 emissions, throughput losses, etc. Online diagnosis of causes of fouling, providing actionable insights that minimize fouling, so operation of flow split, for example, or crude blend operations. Planning heat exchanger maintenance in advance, being proactive versus being reactive, and optimizing the type of cleaning actions to be performed. So being prescriptive on which type of action needs to be taken. So again, all these capabilities hinge on the ability of predicting fouling accurately as a function of operating condition, fluid composition, and time. If we look again at the case study we considered before, this is an already extremely well-managed refinery, as you will see from the data. What we did here is to take the plant data, build a digital twin that represents the network, assess the past performance, train and validate the models so that we are confident that they are predictive, and then assess how the refinery was operated, what can be done from an operational point of view to improve economics, and what benefits can be obtained by implementing a predictive and prescriptive maintenance practice in the refinery itself. So this is a summary of the scenarios that we have considered for the case study. The base case is the actual cleaning schedule implemented in the refinery. And we compare this to a number of other scenarios. First off, the no cleaning scenario. Here we looked at what would have happened if no cleanings were performed. We then considered the scenario in which we optimize the flow split only without performing any cleaning action. The next up is the optimization of the cleaning schedule only without modifying the flow split, so keeping the flow split fixed. And the last one was the simultaneous optimization of the cleaning scheduling and the flow split. So looking at the base case and the 5 heat exchangers in the network considered for the case study, this is how decisions on which heat exchangers to clean and when to clean were made by the refinery. Essentially, they were monitoring the heat exchangers one by one using the fouling resistance, and when certain levels of fouling were reached, they decided to open up and clean that specific heat exchanger that was reaching that specific value of the fouling resistance. Not only this method is based on the fouling resistance, which is subject to the limitations that we have seen before, but these decisions are essentially based on experience. Although they still provide significant benefits, as we will see now, they are not optimal. This is a very simple heuristic that led to perform 17 cleaning actions over 4 years of operations, for a total operating cost of $66 million, with the cost of cleaning representing 1.3% of the total costs, and the rest being fuel consumed in the furnace and costs associated with CO2 emissions. As you can see from the cleaning schedule implemented by the refinery, they were using both mechanical cleaning in blue and chemical cleaning in red. In some cases, the chemical cleaning were not effective. For example, in E04, they had to perform a mechanical cleaning action only a few months after they cleaned chemically. In other cases, chemical cleaning were actually quite successful. So clearly selecting the right type of cleaning depending on the status of the heat exchanger is very important. By using our digital twin to assess alternative technology, the first thing we wanted to verify is what would have happened if there were no cleaning performed. This tells us how successful the cleaning actions implemented by the refinery were. As you can see from the table, the cleaning schedule implemented brought about $2 million savings over 4 years of operation over the no cleaning scenario. It is to be noted that the furnace was assumed here to be significantly over-designed. Therefore, the furnace limit was not hit even in a no cleaning scenario. This assumption allowed us to compare apples to apples and show the benefits of the various scenarios without the production losses, which would have skewed the results. Considering the actual furnace limit, the losses were estimated to amount to over $30 million with the no cleaning scenario. And in fact, they would have had to stop operation for cleaning way before the 4 years due to the hydraulic limits being reached. The next scenario we consider is what happens if we optimize the flow split only without implementing any cleaning action. Typically, refineries optimize the flow split to maximize furnace performance, which means they tend to provide more flow to the branch that is performing the best, so that the enthalpy balance before the furnace is optimized. However, this disregards any effect on the fouling behavior in the train. If you're steering flow from one branch to another, the velocities in that branch drop, producing more fouling. So in the long run, that branch will perform worse than it could or should. For this reason, when we do our optimization of the flow split, we consider not only the enthalpy balance before the furnace, but also the impact of an adjustment in the flow split on the long-term fouling behavior. Thanks to the use of the digital twins and the predictive capabilities of the models, the optimization will take into account all the interactions in the network and provide the optimal long-term operation settings for the plant. In this case, we estimated potential savings by simply optimizing the flow split without any cleaning actions in the order of $500,000 for 4 years of operations. This may not look much, but it is a zero-cost option, and as you will see, when combined with optimization of the cleaning schedules, it can become very powerful. The next scenario that we looked at was the optimization of the cleaning schedule by considering optimal cleaning actions and methods. We provided prescriptive maintenance indications on which heat exchanger to clean, when, and with which method, mechanical or chemical. Chemical cleaning, as we have seen from the previous example, can provide mixed results, but if used properly can be very powerful as it provides a cheaper and quicker alternative to mechanical cleaning. This optimization led to identifying over $2.6 million additional savings on top of the $2 million already obtained by the refinery. This was the result of a combination of an increased number of more targeted cleaning actions, i.e. more frequent cleanings of E01, which led to an increased cost of cleaning, more than twice as much, but to a significant reduction of fuel and CO2 emissions. However, this only considered the optimization of the cleaning schedule at a fixed flow split. If we now consider the simultaneous optimization of cleaning schedules and flow split operations, we can see how the flow split is adjusted based on the cleaning actions taken. While the heat exchanger is taken offline from one branch for cleaning, the flow split is adjusted in order to compensate for this change in the network. When the heat exchanger goes back online, the flow split is adjusted again. Optimizing both flow split and cleaning schedules at the same time not only allows reducing by 3 cleaning actions compared to the previous schedule, but also allows savings about $2 million additionally in fuel alone. The overall result of this is an improvement of $4.3 million over the cleaning schedule implemented by the refinery, so essentially over $1 million per annum. Here is the summary of the various cases considered, showing how better targeting cleaning actions can lead to significant savings over an extremely well-managed refinery. It also shows the money left on the table if you don't implement any cleanings, as is the case for some refineries, perhaps because they don't have bypasses that allows them to clean without shutting down the entire train. The cost of doing nothing in this case is huge. I hope I showed you today in this webinar how heat exchangers fit in the Industry 4.0 revolution. We now have the tools to harness the power of data and advanced algorithms that can be deployed in the cloud to deliver solutions that drive significant bottom-line benefits. And while heat exchanger design and operations have largely been neglected in the Industry 4.0 revolution, improved design and predictive maintenance of heat exchanger networks can help us unlocking increased production, savings due to reduced fuel consumptions, and significantly cut CO2 emissions. With this, I'll stop and take any questions.
Thank you very much for a very interesting presentation, Francesco. That is much appreciated. As chair, I'm now reaching out to our audience. Please do send us your questions in follow-up of the webinar you have just listened to. You may have some dedicated questions for Francesco. Please feel free to send them in. If I may start the question and answer sessions with a warm-up question for Francesco. You talked obviously about predictive and prescriptive maintenance. Could you explain the difference a little bit more in detail, please?
Yeah, sure. Let's start from the beginning. We all know about preventative maintenance, which is essentially we're relying on manufacturers to tell us, for example, for our car, when to do maintenance to our engine and when to replace our tires and so on. Predictive maintenance is goes beyond that in that it uses models to predict the performance of certain equipment, in this case the heat exchangers, and by doing that, essentially it detects the conditions of the equipment and it tells us when to clean that piece of equipment. The step up from this is really prescriptive maintenance, which is essentially tells us not just when to clean, but also how to clean. So which heat exchanger to clean, when to clean it, and how to clean it. So it's prescriptive in the way that what are the actions that need to be taken in order to be effective in objective you want to obtain. In this case, optimally manage your maintenance schedule.
I understand. Thank you very much. You talked obviously about AI and the digital twin. Could you expand a bit on what kind of typical data you do need in order to set up that digital twin?
Well, digital twins, the answer is the more the merrier. The more data we have, the merrier. But we have learned to use very little amount of data. So we use data readily available from typically refineries or other plants, which are temperatures, flow rates, and pressure drops when these are available. If we want to also look at the fluids, we need to have information on the fluids, how the fluids affect fouling. We can do that, but we need to have information on the type of fluids or the type of crudes that have been processed in the refinery, which they're not always available, but in most cases they are.
Excellent. And we have a question coming through from Brunel. Is the fouling prediction data only compatible for shell and tube heat exchanger, or can it be transferred to different types of heat exchangers, such as plate heat exchanger or spiral heat exchangers?
The answer is yes. It can be used in other type of heat exchangers. In the example that are shown in the dynamic retrofit test, in fact, there were different type of heat exchangers. As I said, I cannot say which one is which, but definitely it can be applied to plate heat exchangers, twisted tubes, helical baffles, and so on.
Excellent. Then we've got a question: what software have you used to do the optimization?
We have our own internal software, so we developed our own algorithms, and we use our own algorithms for that. Yeah.
Excellent. And there is a question: have you applied this technology to other industries, for example, HVAC, heating, ventilation, air conditioning, which also is affected by fouling?
We did apply to other industries, not specifically to HVACs. The models are flexible enough; they can be applied to a variety of systems. So I don't see why not. We could not apply to that. But for the moment, the real applications are refineries, petrochemical complexes, and others. So we have been looking at water fouling, for example, but it's all in the process industry so far. But the models and the methodologies and expertise can be applied to also other systems.
Excellent. And maybe a question that is partially linked to that one. We've got a question coming through from BEA Systems. What condition monitoring methods can be used for assessing fouling rates on HVAC condensers on seagoing vessels?
So our analytics tool is very generic in the way that we collect the data, we analyze the data, and it's very flexible. So we are not really too much concerned about the specific industry. When you need to be predictive, then that's where you need to be more there to have a more specific domain knowledge on what is the type of system that you are looking at. So in terms of condensers and seawater and so on, it's something that can be applied. We have condensers models, but it's something that we have not looked at specifically. The way we will approach this is by collecting data, if available. If not, there is very little that can be done. But collecting data and running our deep analytics on this, and look at the fouling rates and try to relate the conditions that generated fouling by using the analytics, essentially.
Excellent. Then we have a question coming through from Siemens Industrial Turbo Machinery. Can you envisage such methods and technologies to be applicable to other industries and equipment? Can you see any challenging blockers for this approach?
Yeah, so as I mentioned, we did apply to other industries. It can be applied to other industries. The main challenge here, and that's what I mentioned during the webinar, is that the tendency in the Industry 4.0 is to just throw AI at a problem. What we have seen that this problem is too complex for AI alone to work well. So the stumbling block there is that we need to better understand what are the system, what are the specific conditions in which fouling happens, have a better understanding of the fouling mechanisms, and apply that knowledge to the data, and then we can use the AI and deterministic models to to solve the problem. So the stumbling block really are the quantity of data and the amount of knowledge that has been accumulated into that specific type of industry.
Excellent. And then we're still all looking at your last slide showing the crude oil or fouling book, but we've got a query in what kind of books for references. Is there anything you would recommend in particular to our audience?
Well, not to advertise myself too much, but yeah, sure. The crude oil fouling.
In addition,
book,
I guess.
In addition to that, yes. So that's specific on crude oil fouling. There's a very good book from BOT, more generic or more open, more different systems. And there's a lot of literature as well in the open literature of various articles and so on. But I would say if you want to start off with just the fouling area in general, I'll say the book from BOT. There is something also on Heat Exchanger Design Handbook, quite detailed and quite broad. So those are probably the two places where I would really start from.
Excellent. And then our colleague from Brunel sent in a second question. For predictive maintenance, do we monitor the inputs and outputs of the heat exchanger, or do we need to monitor for each fixed increment of the length of heat exchanger?
Well, it's practically not feasible in the process industry to have distributed measurements inside the heat exchanger. So it's unlikely that that measurement is available. If it were, we can definitely use it with our models. But what we have seen is that input and output for now provides information good enough to be able to set up our digital twins and so on. As I said, if that information will become available, maybe for experiments and so on, that can also be used.
Excellent. Then we have a question who says, what type of cleaning is recommended for shell side heavy hydrocarbon liquid service? Somebody coming from the recycling technology, so a very, very specialized question for you.
Right. Well, there is the tendency, at least in the oil refineries, is that the default way of cleaning is hydroblasting, and as we have seen from the slides, that provides obviously very good cleaning, but it has some drawbacks. You need to take offline the heat exchanger for a long time. You may spend more money in fuel while the heat exchanger is offline, and so on. Chemical cleaning, thermal cleaning have been applied very successfully to a variety of heat exchangers. But they do have mixed results. So they need to be applied properly and when it's appropriate to use them. In this case, shell side is typically difficult to clean, and if you have heavy hydrocarbon liquid services, they may tend to be very organic material. So thermal cleaning, for example, could be a good option in this case, but also other chemical cleaning, mechanical cleaning can be adopted. Ultrasound as well could be a good option.
Excellent. Then we have a challenging question for you, Francesco. You have obviously shown that velocity and temperature can reduce fouling, but could you advise on recommendations for different heat exchangers?
Yeah, I mean, the issue with fouling is that, as you've seen, it's always a combination of mechanisms that want to deposit fouling on the surfaces and mechanisms that want to remove fouling from the surfaces. Using high shear has been shown that you tend to either prevent fouling to attach because you're removing it before even it attaches, or once it's attached, if you step up your flows, you increase your shear stress, then you're removing the fouling from the heat exchanger. The problem with that, which I mentioned very briefly, is that if you design a heat exchanger with high shear, that creates increased pressure drops. And when you have a network which is already hydraulically limited, and you take off one heat exchanger and you put a different heat exchanger with a higher shear, that may equate in loss in production. And so people are very wary in changing the type of heat exchanger and so on. So that's why we do the study, the dynamic retrofit test, because we want to make sure that when we design for high shear, increasing the velocities and so on, That's where we make sure that the new heat exchanger, first of all, does not create any loss in production, and second, it actually provides a significant benefit to the refinery.
Excellent. Then we've got another question from someone in BAE Systems, a different person, and I presume the answer you will be answering with a yes. And the question is, have you ever looked at coatings that can be used in heat exchangers with regard to fouling prevention or reduction, and this cost when compared to cleaning costs?
Yes, we definitely, as you mentioned, yes, we looked at coatings. Coatings can be applied very successfully, and they do provide a significant benefits compared to the cost of having to open up the heat exchanger, clean it, which also has some safety implications very often, downtime, and so on and so forth. However, coatings are not available for all possible applications. And especially when you start talking about heat exchangers at 300 degrees C, 30 bars, high temperatures with hydrocarbons in a very corrosive environment, it's difficult to find a heat exchanger coating that will fit the bill. So, for example, the application I showed today, heat exchangers at very high temperature, it's unlikely that you find a coating that will work. But in other applications, they can be used very successfully. For example, I'm aware of some pilot studies done in offshore platforms. But clearly, opening up the plate heat exchangers, it's a very exercise. And they're at lower temperature, although the environment is quite harsh, there are coatings that work pretty well on that specific application. So it really depends on the application, but if they can be applied, they can be a very good solution.
Excellent. Then that brings me, apart from a couple of managers, we received very positive feedback on your seminar, people thanking us for that contribution. Some people have inquired about the lecture slides, whether they will be available. These questions will be covered by our IMechE staff. But that brings me to our final question that has been submitted via the system, and it is, of course, maintenance is an important thing to avoid the effects of fouls, but which is the most or main cause of foul that we can reduce or avoid so that we can predict the problem in future in order to solve it?
That's the million-dollar
very
question.
Tricky question.
So there are, if you look at literature, there are categorization of fouling mechanisms. There are 5 different types of fouling mechanisms, and each of them is very complex. So a better understanding of each fouling mechanism and a better understanding of what your systems is affected from, is subject to, will definitely help you find the right solution. One solution could be the coating, the cleaning maintenance scheduling, all ranges of possible solutions. These are all subject to the type of system you have and the type of fouling that you have. So a better understanding of the type of fouling that you have in your system will always lead to a better implementation of the solution.
Excellent. Thank you. I think that brings us to the closure of our question and answer sessions. However, I know some of you may not have been able to listen to the presentation live, and you might be listening to those retrospectively. If you do have any further questions, please send them into the IMechE, and they will be passed on to Francesco, and then he can get back to you in writing. I hope you very much enjoyed the seminar itself, and I would like to encourage you, keep looking on the IMechE events pages, what other seminars, conferences, lectures and webinars are taking place in the future. And thank you all very much for attending today's webinar, and a particular thank you to Francesco for your contribution. Thank you.